Amidst the swirling symphony of angular momentum, the Clebsch-Gordan coefficients take center stage, revealing the quantum world's harmonious overtones. In this problem, what we're tasked with doing is to verify equation 4.175, which was the S1 triplet state when we're adding two spin 1/2 particles. Notice here that we have the coupled bases here, and that equated to an up-up arrow. The coupled bases here, up, down, down, up, so that's a superposition. And then, or a linear combination, same idea. And then here we have another state that we have to verify. Similarly, we want to also verify equation 4.176, which is the singlet state for 0, 0. But this time, instead of using the operators, we want to use the Clebsch-Gordan table. This will be a lot of fun, but it takes a lot of digging around to get used to this table. So by the end of this video, you will know how to read the table for any given coupled state and understand how to get the data you need from it, and of course work forward and backwards on it. But that being said, there is a lot of notation with this. So before we begin, just remember there's a free companion PDF for you to follow along with, and with the given notations that we have, it might be in your best interest to have that with you. But you can access that using the link below, and now we'll get started. So for step number 1, we may as well talk a little bit about what are the Clebsch-Gordan coefficients. Well, we see that with this nasty C notation, what we're trying to do is add together two particles with whatever type of spin they want into a single number, which represents how they're combined in a linear combination with respect to the allowed selection rules. We saw that using the operators, this became a little tedious calculating the eigenvalues and so on and so forth. So a couple combinatorial found and bounded physicists were able to come up with a kind of clever construction and table for all the possible states, which we'll see in the next slide. However, what we need to note here is that these are very important to quantum mechanics at the more structural level because it's a systematized way to approach this and has a lot of work with the angular momentum combination theory, which is kind of applied group theory. And so I'll go ahead and post more properties and kind of background on this on a Patreon post or even the community tabs of this YouTube video. But be aware, there's a lot more than what this kind of just how to read the table video will have in store. So if you want to study quantum mechanics in even further depth, definitely be aware that this comes up again in the group theory aspect. And in fact, I believe that in this book they said something to the effect of, in the mathematical sense, this is all applied group theory. What we're talking about is the decomposition of a direct product of two irreducible representations of the rotation group into a direct sum of irreducible representations. Here, this is the direct product that we're aiming to find from two irreducible representations, S1M1, S2M2, of their respective rotation groups. Again, different type of spin couplings that can happen, but then we turn a direct product into a direct sum, again with the selection rules adding on. And again, we see that we come from two individual states here, S1M1, S2M2. And so just be aware that there is a lot of fun stuff that can be done with these, but they're definitely messy. I'd also like to take a second to reiterate the fact that there doesn't seem to be a set notation for all of this stuff, and it's kind of annoying going from textbook to textbook and seeing the different representations. I try to combine them all in the different letter types that they use. Some use capital S, some use capital J, and lowercase j for the individual states. It all depends on your text, so I try to give you a couple more in the PDF, but didn't want to clutter this video. But nonetheless, very important that we understand that this has a lot of weight and further aspects of symmetry, rules, all those fun things that we get from the group theory aspects in the reconstruction. But beware, there's a clever way just to get it done. This is a very mechanical video, so we'll go ahead and see what this table is and learn how to dissect it. Okay, so given the fact that we have several types of spin now. Again, this is different from the orbital angular momentum in the fact that it's not just integer spins, but half integer spins. So up here, which is the one we're studying, is the 1/2 by 1/2 interactions that could be possible and all the different conjoined coupled states. Here, of course, we could have 1 and 1/2, 2 and 1, 1 and 1, 3/2 by 1, 3/2 by half, and 2 by 3/2, or 2 by and a half. All of this is just a combinatorial nightmare, and this table just allows us to kind of breathe through it. This is actually from the book, so you can feel free to look that up. If you want the book, again, the Amazon links are down below. It's another great way to support the channel if you would like. But as you see, this table is not exactly just easy to read off. It's not something you can plug in Excel and just, give me this output for this, although you could definitely program it. And in fact, one of our professors made us program this, so it's possible, but not the easiest. It's easier just to read off what this table is representing. So we'll go ahead and dive into that right now. Okay. Stop number 2 then, we first need to see how to read the table. What I want you to highlight here is that in the upper box, which is these boxes here, we have the coupled state S and M, meaning that this is the combined state that we have. And here on the lower left box, we have the individual M states, because up here we had the S1 and S2 states for whatever we were looking at. To describe that, this is the S1, S1, or S1, S2 states for the whole table. So that's taken out, and we don't need to worry about that. But we know that those combined states are left with the selection rules on the M numbers, the quantum numbers for M, because M was dictated based on what S was. That being said, we need to first realize that for what we're trying to do, each one of these selection rules has a specific amount of coefficients that can be used. Again, these are representative of the type of linear combinations we can have, but one of the rules is that their squares have to all add to 1. Remember, we're still in quantum mechanics. We have to be normalized and all that other good stuff we learned. So just be aware, as we see when we get clunky tables, these are the coefficients that we're reading off, and they represent how the linear combination adds together. And again, these are the coupled states up here that we need to verify. And these are the quantum numbers M1 and M2 respectively. That being said, let's go ahead and dive into the first combined state, which is 1 and 1. Notice that of the 4 combined states that can be there, or the coupled states, we need to focus on just the 1 and 1. So we'll go ahead and highlight that in our next slide. I find it easier just to actually highlight it all because the tables are just a mess, very messy, and it's just a headache. Again, S1 and S2, we don't need to worry about because that's the individual table that we selected out. That being said, we know that for the first coupled state, we want the 1 and 1. This is big S, this is big M. So that's the vector here that we're trying, or the state that we're trying to show is in the tripled state given to us. That being said, this is the column as denoted with the underbrace. This is the table in this specific representation that Griffiths and forgot the other guy's name, but in this book, this is how they label it. And then what we need to do is read off that for this coefficient, these are the M states allowed for this coupled states. So we write down what came from the row. That being said, one of the rules in reading the table is that everything is under a square root. And if you see that there's a negative on it, which we will later, then the negative goes outside of the root. So simplifying this down now, we can go ahead and drop all the positive signs because we kind of know what's going on. And we see that the square root of 1 just goes to 1. So our normalization is still intact. And we see that this is the S1, this is the M1, so that can go and cooperate itself to state 1 here. Again, different text, different notations. I'm just trying to make you aware of everything that's allowed, everything that I've seen, and surely there's more coming up later. Then the second indices for the coloreds are S2 and M2, so that's the second state here. And in this context, what is defined in the book and what's in the PDF is that both of these are spin up, so we use up arrows for both, thus verifying the first state that we were trying to do, and so we get through our first checkpoint. That being said, these get more complicated pretty fast as we see the second box looks a little looming and dooming, and then we get to the third box. Let's go ahead and see what our next stop is. Wonderful. That being said, I'm not going to highlight this again because we saw that we already had this from the table here. But what we need to do is realize that we're looking for the state 1, 0, which was the next state given in that triplet set. So we look at the column that has 1 and 0. That's this column. Next, we see that this coefficient for this column, because that's all we care about is this column, this coefficient is for the state with +1 and -1/2. So this comes to row 1 here. +1/2, -1/2. This is the table that we're using. Again, we also have a second coefficient here, so we need to involve the second row, and we label that here. After that, we see that the square root of 1/2 just goes to 1/√2 because we don't like to rationalize, but both of them have the same square root, so we can factor that out. Now, if we decompose this into the two independent states, we get a plus plus, that gives us an up arrow, a plus minus, that gives us the down arrow, a plus minus, down arrow, and a plus plus, so an up arrow, thus verifying the second state that we needed to in this first triplet. The final one in this triplet will be next. So finally, to stop number 4 then. Now I'm not going to highlight anything and we could test ourselves. First things first, let's see what column we need to reference. 1 and -1. So that's this last one here. Okay, cool, that works. So we have one coefficient here, and that is correspondent to these two magnetic numbers. So we have -1/2 and -1/2 put here from the row, and we're good to go. Notice that square root of 1 gives us 1, so we're good to go there. And also note that the combined state of square root of 1/2, squaring them together, you get 1/2 plus 1/2, so that equaled 1, so our normalization is good there too. But here, again, from the table, positive, positive, negative, negative, so this one and this one gives us a down arrow. This entry and this entry give us another down arrow, so we once again verify exactly the last set in that triplet state that we need it to, and we're good to go. But while we're here in this completion of this first triplet state, or equation 4.175, let us note here that if I'm given the magnetic numbers here, or the m sub s, I can also go backwards and find a coupled state. This is another property of the table that we could work from a row, and whatever the row is gives us the adjacent column, and that's what we work with. This is a two-way table. It's very clever construction now that we're kind of dealing with it. And I believe Griffiths also acquainted this to, or made an analogy to driving a stick shift. It's kind of messy to start with, but once you get the hang of it, it's not as bad as it first looks. That being said, we still have one more state to prove, so let's go ahead and finish this off and be glad that this table exists so we don't have to find every state by hand. All right, now to our final stop. We need to prove the singlet state. And again, based on the selection rules, to get 0 here and here for the magnetic numbers where we have to add them, we need to add something with a +1/2 and a -1/2 because that gives us 0. So, but we could also have a -1/2 and a +1/2. That gives us 0. So that's why we have all these weird normalizations here. But again, since our s is 0 here, we need the combined coefficients here to cancel in some form. So this is a pretty clever table all in all, and just has a lot more packed into it than what is originally presented in the introduction text. So be aware, there's a lot of great papers on it, and I think I'm going to review one of them if that's of interest. I'll post that on Patreon though, because it's a lot of work to dive into them and write the report, but it's also a lot of fun. All right, nonetheless, what we see here is that we need this column. So we see that this positive 1/2 is associated with M1 is positive 1/2, M2 equals negative 1/2. Positive, negative, and a positive square root. Here's the part where the negatives come in on the coefficient box. This negative goes outside of the square root, but then we put the number inside the square root. So although this table is pretty clever, the square root and the negative signs are the only thing that throw it off. Be aware that is implied when using the table, and this is how you use it. But that being said, this negative 1/2 corresponds to this row. So we have a negative 1/2 and a positive 1/2. Thus, once we see that both of them have a square root of 1/2, we can factor that out here. Just note that the minus sign still stays on this combination of the second states. So we have S1, M1, positive, positive, up arrow, positive, negative, down arrow, positive, negative, down arrow, and positive, positive, up arrow, thus verifying the singlet state or equation 4.176. Pretty cool, I would say. Pretty cool. In summary, then, we now know how to use the Clebsch-Gordan table to find the coefficient for the states, as well as how to, in the last video, how to use the operators to also find the states. We verified both methods. Eventually, you'll see whatever you like and use that for whatever problems may come up, but at least you have more tools available now. Again, a massive thank you to our patrons for their invaluable support, which is making all of this possible. Please consider subscribing and sharing to fuel this curiosity, or even becoming a patron yourself. New content is posted weekly to aid you in your curious pursuits. Thank you, kind people. Books, notes, and other reference materials are found below, and of course I'll upload more to Patreon or the community tab because this stuff is just so cool. If you have any questions, please feel free to reach out. This isn't always easy, but it certainly is fun. As always, thank you for watching, and until next time, stay curious.